In this video, we'll be talking about capacitors in series and parallel circuits. So let's make a list of things that determine capacitance. What kind of things affect the capacitance of a capacitor? Pause for a second, make a list. We should include area of plates, distance between plates, if there's a dielectric, and all of those go together to make the equation for capacitance, which is kappa, which is our dielectric constant, times epsilon naught times area over distance between the plates. So we need to keep these things in mind, especially area and distance between the plates, as we're thinking about combining capacitors and circuits in parallel and in series. So here is a circuit, and in the circuit I have a 5-volt battery. It is connected in parallel with two capacitors, capacitor 1, capacitor 2. The capacitances of capacitor 1 and capacitor 2 are equal to each other. So let's think about what we know about circuits. What is the potential at position A, B, C, and D? So think about that to yourself right now. And you should have thought that A and B are connected to the positive plate of the battery with no resistors or anything in between. So they should both have a potential of 5 volts. C and D are connected to the negative side of the battery with nothing in between, and there's only one battery, so these should have the potential difference of 0 volts. So we're going to see that we have the same rules as we had for resistors. These are going to follow, capacitors are going to follow that same rule, where if they are in parallel with a battery or with anything, they're going to have the same potential difference as that battery or whatever is there. So now let's think about the next question. Will the capacitors have the same charge? And the answer should be yes, because we use the equation Q equals C times delta V to determine our charge. And that comes from the equation for capacitance, and capacitance is equal to charge per voltage, so Q over delta V. So if we multiply each side by delta V, we get Q equals capacitance times delta V. So since they have the same voltage and they have the same capacitance, they will have the same charge. The next question is, what is the resulting capacitance? Well, basically, if we think about our equation for capacitor, which is kappa times epsilon naught times A over D, effectively what we're doing here is increasing the area. We have twice as much space for those charges to occupy because we've added another capacitor in parallel. The potential difference is the same across each plate. We've just doubled the amount of area on which we can store charge. So the capacitance for this is going to be 2C. It's going to double our capacitance because the capacitors are the same. So if we were to write an equation for the equivalent capacitance for capacitors in parallel, we would just have C1 plus C2 plus C3, and then however many capacitors you have in parallel. Now let's talk about the rules for series. So as we think about this, let's think about what the charge will be. So we have our 5-volt battery again. We have one capacitor here, two capacitors, the second capacitor here. They have the same capacitance once again. At point A, B, C, and D, we need to think about what the charge will be at these points. So what's going to happen here when it's connected is the positive charge is going to spread out from the positive side of the battery and spread onto this plate. So this plate is going to get a positive charge. This plate is going to get a negative charge. Then this plate will get a positive charge and this plate will get a negative charge. But basically what's happening is this piece right here is not connected to the battery. So this piece right here polarizes. So that you have the same negative charge here as positive charge here, and same positive charge here as negative charge here. So that's an important part there. Our next question to think through this is, how do points B and C get charged if they're not connected to the battery? I already answered that one. They polarize. So what happens is this effectively makes our two capacitors act like one capacitor, but we're increasing the D in our equation. I'm going to come up here and write that. So we know capacitance is equal to kappa times epsilon naught times area over D. And D increases. So C decreases. So when we have capacitors connected in series like this, it decreases the capacitance because this middle chunk right here is basically just polarized, and it's separating the same amount of charge. So we want to write an equation for adding capacitors in series, and that equation is CQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3 dot dot dot, and then the inverse of that. That should look familiar to you because that's the same equation that we used for adding resistors in parallel. Notice that the equations are switched. So for resistors, when we added them in parallel, we used this equation, but for capacitors, when we add them in series, we use this equation. And then for resistors, when we added them in series, we use this equation, but when we add capacitors in parallel, we use this equation. So they're just the same rules, just flipped. Next page, some important capacitor rules. For capacitors, Q is going to be the same for capacitors in series. And this is because of this polarizing effect, right? We know that a capacitor is always going to have the same positive charge and negative charge on the two plates. It's the same amount of charge. So if this one gets a positive charge Q, this one has to have a negative charge Q. Well, since this middle piece is polarizing, the whole thing is neutral. So if this gets a negative charge Q, then this is going to get a positive charge Q. And then that's going to be the same as this. So anytime capacitors are in series, they're going to have the same charge. Now let's talk about charge in parallel. In parallel, they're going to add up to the total charge. So here's our parallel circuit. If this entire circuit separates a certain amount of charge, then part of that charge is going to be on this plate and part of that charge is going to be on this plate. So the total charge separated will be this plus this. So the total charge is going to add up. To get the total charge, you add up the charge for all the different capacitors when you're working with parallel. Now let's talk about delta V. Delta V follows the same rules as it did for resistors. And we already talked about that a little bit. Delta V is the same for capacitors in parallel, and that's because their sides are connected to the same point, and so they're going to have the same potential on each side. And then delta V is going to add up for capacitors in series, and that's also conservation of energy rule, our loop law, and we just know that we have to add up to the total for any loop. So here, if we had a total potential difference of 5 volts, we would have 5 volts of potential here, and then since these capacitors are the same, we would have 2.5 volts of potential here and 0 volts of potential here. Okay, so let's do an example. I have drawn a kind of sloppy, sorry, circuit here. And we have a 10-volt battery. We have a 3 farad capacitor and a 2 farad capacitor in series. And then those are in series with a 6 and a 12 that are in parallel with each other. So we're going to use very much the same methods that we used for resistors when solving these, where we combined components slowly together and then worked backwards from there. So I'm going to follow all those steps. And as you get better at this, you might be able to skip a few steps, but for the most part, it's probably best to start off by redrawing the circuit. So I can see that this is in parallel. And so I'm going to know that I'm going to use my equation for CEQ is just going to be 6 farads plus 12 farads because they're in parallel, so you just add them. So we get 18 farads for that part. Now my circuit is going to look different. Now it's going to have a 10-volt battery here. It's going to have my 3 farad capacitor, 3 farad capacitor, and then a 18 farad capacitor. Now it's important to note that when you're drawing these diagram symbols, the battery has the short line and the long line, and the capacitors have 2 equal lines. So be careful to make that apparent when you're drawing things. 3 farads, and that's 2 farads, and this is 18 farads. Now they're all in series, so CEQ is equal to 1 over 3 plus 1 over 2 plus 1 over 18 to the negative 1, and that gives us a CEQ of 1.125. I'm just going to round to 1.13 farads. So that's our equivalent capacitance. Now, just like when we were solving problems with resistors, you would find your equivalent resistance and then use that with your voltage to find your current. We're going to use our equivalent capacitance and use it with our voltage to find our charge. So it's a very similar process. You're just solving for different things. So we know that the total charge separation, so this is total, is equal to the capacitance times delta V. So we have 1.13 farads, and we multiply by our delta V, which is 10 volts, and that gives us 11.3 coulombs of charge that are separated. So that is an important number there, our total charge. Now is when we start moving backwards. So we know that these 3 capacitors are in series. So since they are in series, if we go back to our rules, we can see that charge is the same for capacitors in series. So if this whole circuit separates 1.3 coulombs of charge, then we know that we have 1.3 coulombs of charge for each of these. So I would have, for my 3 farad one here, I need to find my voltage. And to do that, I would do delta V equals Q over C. And my charge is the 11.3 coulombs. And then I divide by my capacitance, which is 3 farads. And that gives me 3.75 volts. Then my 2 farad, I have, again, delta V equals Q over C. So my charge is 11.3 coulombs. My capacitance is 2 farads. So that gives me 5.6, I rounded these differently, but 63 volts. And then my 18, I have delta V equals Q over C, which is 11.3 coulombs divided by 18 farads. So that delta V is 0.63 volts. So now I have my voltages for each of these. Now I would recommend, much as we did in problems with the resistors, making a little chart with capacitance, charge, and delta V, just to kind of organize your stuff, because a lot of times, especially in the table problems that we're going to do, you're going to have a bunch of capacitors, so it makes it easier. So we have a 2, a 3, a 6, and a 12. And 12, and charge in coulombs and potential difference in volts. So we have solved for the 3 and the 2, both have 11.3 coulombs. And then the 2's voltage is 5.63. And the 3 farad capacitor has a voltage of 3.75. And then we have to figure out the other two, although we do know their voltage because they're in parallel, right? So we're going to work backwards. They're in parallel, so they have the same voltage, which is 0.63. Now, we can also double check ourselves throughout this, because we know that the voltages should add up to the total voltage when they're in series. So 3.75 plus 5.63 plus 0.63, that's right at 10. So that kind of helps us know that we have done it correctly, which is great. All right, so then now we're going to move up and find the charge on each of these for this one. So now for my 6 farad, oops, I don't want to be black. Okay, so my 6 farad capacitor, I'm looking for my charge, and charge is equal to C times delta V. So I have 6 farads times my delta V, which was 0.63? Yeah, 0.63 volts. And that gives me 3.75 coulombs. And then my charge on my 12 is capacitance times delta V, so that's 12 farads times 0.63 volts. So that is equal to 7.5 coulombs. So I can do 3.75 and 7.5 coulombs down here. And now I can, I have all my numbers. Now we can also double check ourselves here. We know that these two need to add up to our total charge, which was 11.8, 11.3. I was like, that doesn't work. 11.3, which it does, so that's good. And then that's how you solve the problem. It's a little messy, but it works.